Hi, everyone. Thanks for joining me today. I'm Kerry Halupka, a principal machine learning engineer at Canva. I'm excited to share our journey in scaling content understanding systems to handle monstrous volumes of images, over 40 billion, in fact. Let's dive right in. I've spent my career designing and scaling high-performance systems in AI and distributed computing. My journey spans across real-time processing, automation, and extreme scalability, which has led me to mentor teams and share knowledge with the broader tech community. At Canva, my focus is on advancing ML capabilities for content understanding and supporting millions of users globally. Before we dive into the technical details, I wanted to give you a quick overview of the challenges that we set out to solve. Canva has been growing exponentially over the years. This chart tracks monthly active users, now well over 220 million users globally. We're present in 190 countries and we support 100 languages. With that comes an incredible volume of user-generated images. This growth drives our need for highly scalable pipelines that can label and organize this ever-expanding dataset. Our platform handles around 40 billion images in total and is ingesting between 50 and 100 million new images every day. That's a monstrous influx of content. To provide value like search, recommendations, and personalization, we need accurate, real-time labeling at scale. The system we designed had to be accurate, real-time, and flexible enough to handle newly emerging labels without significant downtime. But equally important, it required a curated dictionary of labels, not just open-ended text tags, to ensure consistency and prevent confusion when new concepts appear. You see, as humans, we automatically recognize nuanced concepts like work-life balance or father-son bonding, even from a single image like this. It's not just about identifying objects, it's about understanding the context and meaning. But training a machine to capture that nuance is complex, especially when we're dealing with tens of millions of new images daily. See, machines traditionally handle more literal tasks, detecting basic objects like person, toy, truck. While these are valuable, they don't capture the richer contextual meaning of an image. Our goal is to push machines beyond identifying simple objects and closer to the nuanced understanding of a human. Let me show you what this means in practice. If I search for energetic business meeting, which I don't know about you, but I search for that kind of thing every day, we don't just want images of people in suits around a table like we see on the left here. We want to understand the energy, the collaboration, the problem solving, the excitement happening in that room. We want to find images that capture that specific mood and moment, even if nobody explicitly tagged them with those exact words. Early on, we saw huge gaps in search results. Sometimes the system either overlabeled images or missed key concepts entirely. You can see here that while these images on the left are in fact all business meetings, they're not what I would call energetic. These images only halfway address the user's requirement. We needed to go deeper, empowering our content understanding pipelines to recognize more nuanced concepts. See, in building a content understanding pipeline, you wrestle with two dimensions of complexity: the sheer volume of images and the depth of conceptual understanding required. We need to scale in both, which is the key to making the system truly valuable to users. Imagine a pyramid of concepts. At the bottom, you have simple objects like person, toy, truck. And then in the middle, you move up a little bit to slightly more nuanced and complex concepts like playing and father, parenting. And then at the very top, we reach abstract human ideas that can't specifically be labeled to a precise location in an image. It's more about the vibe, like work-life balance and father-son relationships. This is the depth that we needed to teach the model. All newly introduced concepts become part of our established label dictionary, ensuring that we don't rely on arbitrary free-form tags. Consistency in label definitions is critical for maintaining accuracy as we scale. Not only that, concepts that are important to users aren't static. It's a moving target with new trends popping up every day. So we needed a model that could handle thousands of labels and easily expand to thousands more to capture these deeper concepts. When we talk about building a system like this, which we call an extreme classification system because we're talking about thousands of labels here, there are three overarching requirements: cost, scalability, and performance. Cost matters because we can't run overly complex models at the scale of billions of images without costing the earth. Scalability is critical because our system needs to learn new concepts all the time to stay up to date with trends and user requirements. And finally, performance, which translates to model accuracy. We need the right predictions at the right time on the right images so that users can see what they're expecting to see when they search for something. These three requirements, compute, scalability, and performance, guide our design choices. We have to balance them carefully, often making trade-offs. For example, sometimes lowering cost can mean adopting a smaller model, but that smaller model has to be accurate enough to maintain a good user experience. So let's dive in a bit. The compute problem. One way that we tackled this compute challenge was to explore alternative model architectures. Our first breakthrough was to use an architecture that scales efficiently with the number of concepts. We use the ML decoder architecture. You see, traditional classification architectures scale worse than linearly with the number of labels to classify, which leads to massive models that don't learn well when we scale to thousands of concepts. Instead, we use a modified transformer decoder called ML decoder, which scales better than linearly with the number of concepts. This means that we could scale to thousands of concepts without too drastically increasing our model size. I'm not going to go too deeply into this architecture. There's some really great research papers that dig into this if you're interested. The next problem is data, scalability. Concepts emerge all the time like cottagecore, which, if you're not on Pinterest all the time like me, romanticizes a rustic and cozy lifestyle. Think picnics, farmhouses, cozy interiors. This concept was unknown to us at first, so our model wouldn't label images correctly. The question becomes, how do we quickly get new training examples for these emerging ideas without manually labeling thousands of images from scratch? That's where our iterative data labeling pipeline steps in. And it's the thing that allows us to scale to many more concepts constantly without repeating arduous and tedious human-based labeling practices. Our pipeline starts with defining the new concept. So let's say I announced a new concept, which was banana, and I asked you to find every image in Canva's database right now, which shows something to do with bananas. How would you do it? You probably wouldn't look at all 40 billion images one by one. Instead, you'd look for patterns. This is what our pipeline does automatically. We find images that match using a combination of text-based and image-based search. Then we check our entire dataset for additional occurrences. Sometimes previously unlabeled images actually contain the new concept. We label those images, potentially feeding new examples back into the model. It's a feedback loop. Each new concept expands our ability to classify images more accurately over time. One of our breakthroughs, though, was realizing that a single search term like cottagecore might be too narrow. Instead, we use a large language model to generate diverse descriptions of the new concept, which produces descriptions like a cozy farmhouse kitchen, a young woman with wildflowers, a picnic in the woods. These are things that would be associated with cottagecore and you would expect to see if you search for the term cottagecore. By searching using multiple prompts like this, we find a broader set of images that represent the concept. This approach dramatically increases our coverage, ensuring that we don't miss the less obvious but still relevant examples. But I keep saying searching for images, and you might be asking, Kerry, how are we going to search? This is the system that labels images to enable us to search. So that's where we introduce our natural language-based retrieval mechanism. We use CLIP, which can compare text and image embeddings in a shared space. Because CLIP understands concepts more naturally than traditional keyword matching, it can find examples even when they're not explicitly labeled. By embedding multiple text variations, we surface images that we might never find from a single search query. For example, searching for cozy cottage kitchen with vintage decor might uncover images that previously didn't have the word cottagecore explicitly tagged, but visually match that aesthetic. The way this works is that we embed every image in our library using CLIP, and then we embed our new descriptions of the concept, like cottagecore, and we find the most closely matching vectors or embeddings using an approximate nearest neighbor search, which returns to us images that are very similar to our new description, but aren't explicitly labeled as such. However, this returns to us images that we would label with the one concept of cottagecore. But one image can have a dozen valid labels. A cottagecore image like this might also have labels like bread, milk, eggs, cozy. If these labels aren't applied to the images and this image is added to our data set for training, then the model's performance actually declines on these concepts. So we needed to figure out what other labels to apply to each image and assign them. Again, though, we're trying to automate this process to reduce the time it takes to learn a new concept. So we can't have a human labeling these images with the additional concepts. Here is where our next breakthrough applies. After we find a candidate image, we use the label classification model that we're actually training to propose related concepts. But we allow it to propose at low confidence. This optimizes for label recall. This results in a data set that has high recall but low precision, since images are tagged with some labels that are not correct. In this example, the label artistic shouldn't actually apply, but because we allowed our model to label with low confidence, it ended up getting tagged. We really don't want to teach our model with these kind of incorrect labels because then we will reduce the accuracy of the model overall. To improve the precision of this data set, we remove incorrect labels through the use of a visual critic model to validate and reject labels. This ensures that we keep high confidence associations. In practice, we use highly performant visual large language models like GPT-4o. You might ask, why not just use GPT-4o to tag the entire data set if it is this good? Why even train your own model? And the reason is that models like this are too expensive and slow to apply to our entire collection. But we can use them to produce data sets to train smaller, faster models like ours. And using the pipeline that we've designed here, we can also restrain them to a specific set of labels because of our requirement to keep a structured and maintained dictionary of labels. So, putting it all together, whenever we introduce a new concept, we generate multiple text descriptions via a large language model. We use CLIP to find diverse images associated with these descriptions, and then let our model that we're training propose related labels with a low confidence. This produces a lot of labels for each image. We finalize and refine those labels through the use of a visual critic. The outcome is a continuously improving training set that keeps up to date with evolving content and vocabulary and can be used to train small, efficient models that can run at large scale. The power of this approach is that it's both scalable and maintainable. When we need to add new concepts, whether it's cottagecore today or whatever trend emerges tomorrow, this automated pipeline can find diverse, accurately labeled examples without massive manual effort. And because each step is optimized for quality, we can maintain high accuracy, even at massive scale. So remember our challenge from the start. We now have a system that can scale, adapt, and learn new labels all on its own. So to wrap it up, we addressed compute by adopting efficient model architectures like ML Decoder, specifically designed to deal with thousands of classes. We tackled scale by designing a process that automatically finds data that can be used to train new concepts. And we tackled performance with iterative labeling pipelines, using visual critic models and a curated dictionary of labels, to boost accuracy while continuously adding new concepts. Ultimately, these strategies let us handle huge volumes of data without compromising of the quality of our labeling. And that's a wrap. Thanks so much for joining me on this deep dive into scaling content understanding. I would love to hear your thoughts, whether you're tackling similar challenges, have questions, or just want to nerd out about machine learning and large-scale systems. Feel free to connect with me on LinkedIn or just shoot me an email. Looking forward to continuing the conversation. Thanks, everyone.